Information that I wanted you to watch this video on R, the correlation coefficient. It's a quantitative assessment. That means it could be a statistic or a parameter, but it measures the strength and direction of a linear relationship in a bivariate quantitative group of data. Pearson's R is the one that's used the most. If I'm finding a population correlation coefficient, I'm finding a parameter, I look for the Greek, the symbol will be rho. If I'm looking for a statistic correlation coefficient, it's lowercase r. The equation, pretty much what we looked at in class. It's the product of the z-scores for x times the z-scores for y, and it's the average. But instead of dividing by n, if it's a sample, I'm going to divide by n minus 1 because that last dot changes everything. I have 1 degree of freedom. In the first example, I've got 6 primarily undergraduate universities in California with enrollments between 10,000 and 20,000. The 6-year graduation rates Y and the student-related expenditures per full-time students X for 2003 were reported as follows. Create a scatter plot and calculate R. I've put those values on your handout, but we'll enter them into our calculator and find out what they'll be. I go to Stat, go to Edit. I need to enter those numbers into a list. 7, 3, 2, 3, 8, 7, 3, 5, 7, 5, 4, 8, 7, 0, 7, 1, 8, 2, 4, 8, and there's 6 that should be on 7. I'm double checking to make sure the X value is right as I put in my Y values. It's kind of important that you make sure that you don't have any typos, because things go wrong and you go, oh no. Okay. All right, so I create my scatter plot, second stat plot. I want to do it on 1, it's already on. I've got a scatter plot selected. My X and Y list are in list 1 and list 2. I could have named them, but I'm in a hurry. So I'm ready to look at the graph. Oh, I don't see anything. Yes, zoom 9. There's my scatter plot. Okay, and I'm going to be guessing that R is positive and very close to 0. So I go to Stat. I've made sure my diagnostics were on already. Calc 8. I have list 1, list 2 as my X and Y list. I hit calculate, and my R is 0.05. As I predicted, it was positive and very close to 0. So there's the scatter plot, there's R. Let's look at the properties of the correlation coefficient. Property number 1. The only values that R can take on range between -1 and +1. R value of 0 says there's no linear relationship. That's what correlation is going to mean, a linear relationship. From -0.5 all the way up to +0.5, we're going to say it's a weak linear relationship. Between 0.8 and 0.5, between -0.5 and -0.8, a moderate correlation, and between 0.8 and 1, -0.8 and -1, we'll say there's a strong linear relationship, a strong correlation. If I changed those graduation rates from percents to decimals, I want to transform the graduation rates and calculate R. And R is still the same. Why is that? Well, pause, think about it, come back. If you do those transformations and calculate R, the z-scores are going to be the same. Okay? Value of R isn't changed by any linear transformation to your data. Suppose we wanted to estimate the expenditures per student for given graduation rates. Switch X and Y and calculate R. So go back to our calculator, and we're going to stat calc 8. But this time our list 1 is going to be list 2, and our X is going to be list 1, and enter, and surprise, R is the same. Okay? So the value of R doesn't depend on which of the two variables is labeled X. And that should make sense because it comes from the product of the z-scores for X and the z-scores of Y, which wouldn't be, the product wouldn't be affected by switching X and Y. Suppose that 33.9 was really 63.9. What do you think is going to happen to the correlation coefficient? Pause, think about it, come back, plot our revised scatter plot and find R. I go in to my data, I go to that last value and I change it to 63.9. I look at my scatter plot, it looks a little different. I look at my R, change that back to list 1, change it to list 2, and my R is much stronger. So there it is, there's my new one. R is much larger. Extreme values do affect the correlation coefficient. Value of R is affected by extreme values, which is why you need to comment on them in your discussion of a scatter plot. So if I were to find the correlation for those points, I'm going back to my calculator. This time I'm going over to list 3. Oops. -3, -1, 1, 3, 5, 7, 9, 40, 28, 4, 8, 20, 40. Oops, there's something wrong. 40, 28 goes with 3. Nope. -1, enter. 1, enter. 3, enter. 5, 7, 9. There we go. Now they match up. Oh, I'm going to my stat plot. No, let's actually look at our correlation first. Oops. It's in list 3, list 4. My R is 0. Well, you might be peeking at my graph, but if I go to stat plot and I go down, change this to list 3, list 4, graph, zoom 9. I have clearly a relationship, but I have no linear relationship. Okay? So you have to be careful when you're interpreting your correlation coefficient to remember that in fact it's a linear relationship. So to recap the properties of R, legitimate values have to be between -1 and +1. It's not affected by linear transformations to your data. Value of R doesn't depend on which of the two variables is labeled X. It is affected by extreme values, and it's a measure of the extent to which X and Y are linearly related. So if I want to interpret an R value of 0.05, I want to recall the definition. It's an assessment of the strength and direction. there is a weak, positive, linear relationship between expenditures and graduation rates. Does the value of R close to 1 or -1 mean that a change in one variable can cause a change in the other? Well, what if I'm discussing the relationship between the number of cavities in a child's teeth and the size of her vocabulary? I find that it's strong and it's positive. So does that mean I should give children more candy to increase their vocabulary? They're both strongly related to the age of the child. So there's a confounding variable. Consumption of hot chocolate is negatively correlated with a crime rate. So does that mean that we should drink more hot chocolate to lower the crime rate? Big surprise, both are responses to cold weather. Causality can only be shown by carefully controlling values of all variables that might be related to the ones under study. In other words, a well-designed, well-controlled experiment that includes randomization. Correlation does not imply causation. Oh yeah, correlation does not imply causation. Correlation does not imply causation. Thank you very much. Oh, where is it?